Okay, I'm going to go through this paper again. There was a problem with the audio. I'm just going to try and do it. Okay, so this is the Pearson Edexcel Physics Linear Exam for AS level students. It's paper 2 for the AS level. It's called Core Physics 2. It's from June of 2022. Okay. So June of 2022, they didn't put the year on it, but it was used. Okay, so I'm going to run through it as quickly as possible. If you find the videos useful, don't forget to like it and share it with other people you know who are taking this exam. Okay, so question 1 of the multiple choice, which of the following provides evidence for the particle model of light, or the particle model of electromagnetic radiation? And that is the visible line spectra. All the rest, diffraction, interference, polarization, are all to do with the wave model. Okay. Question 2. In the investigation to determine the Young's modulus of steel, in the form of wire, students plotted a straight line graph. The Young's modulus is numerically equal to the gradient of this graph. Therefore, what must they have plotted on each axis? Must be stress against strain, because Young's modulus is the gradient of stress against strain. So there we got stress on the y-axis, strain on the x-axis, so the answer is B. Question 3, which of the following is the SI base unit for the Planck constant? So Planck constant comes in this equation, so you can use it to work out its unit. H will then be joules seconds. So you've got to change joules into newtons times meters, and a newton is kilograms meters seconds to the minus 2, because it's mass times acceleration. Multiply that by meters. There it simplifies. Multiply by seconds for the joule seconds. So you've got joule seconds there. Seconds simplify to kilograms meters, meters squared, seconds to the minus 1, gives you an answer of C. Question 4, the ray diagram drawn to scale. Scale is 1 centimeter per square. The object is 2 centimeters from there, and it looks like a magnifying glass. The lens should be diverging because it's enlarged image. So the image is further away on the same side, so it's virtual. Okay. So which row gives the focal length correctly? So to get a magnifying glass, you want the object to be within the focal length. So just inside, if it's too far, so it's converging, so magnifier, so it's there, and the focal length is just more than the object, will give you a great magnifying effect. Okay, and that's it. The answer is A. Question 5, a student measures the diameter of a steel wire in order to determine the cross-sectional area. The percentage uncertainty in the measurement of diameter is given as 1.8%, and they want you to work out the percentage uncertainty in the cross-sectional area. Well, since the cross-sectional area is pi d squared over 4, then the percentage uncertainty of A will be twice the percentage uncertainty of D, because D comes in twice in terms of the calculations. Each time you use D, it brings 1.8% of uncertainty with it, so it's 3.6% in total for the percentage uncertainty of A, because pi and 4 are numerical values which are known. Here you have a 2-beam oscilloscope used to display signals from 2 microphones, as shown. They're out of phase by 1 square. The period for the wavelength, or the period for the wave, is 6 squares, so the phase difference is 1 square out of 6, so it's 1/6 of 2 pi in radians, because they want it in radians. Okay, so that comes to pi over 3, which is C. Okay. Question 7 shows energy levels for possible energy transitions in an atom. So 2 arrows are going down. Arrows going down are emitting light. So these 2 are emitting light. And arrows going up are absorbing photons. Okay? For some reason it wants to put the arrow down. So these are absorbing photons, the green ones, and the yellow ones are emitting them. Okay, so the question says, which arrow shows the transition made by the electron when it emits radiation? So that would be downward arrow, so it's got to be C or D, and it has the longest wavelength. Longest wavelength means a smaller energy, yeah? So that will be the shorter arrow downwards. So the answer is D. Mark scheme, unfortunately, I've put sideways. It's just that the Edexcel linear puts the paper landscape and the mark scheme. The paper is portrait and the mark scheme is landscape, so it causes a little bit of confusion when I'm making a PDF. Okay, so question 8 we haven't been through. The answer is D. I apologize for that. Normally I rotate them, but it was too late, and your exam's tomorrow. So 8 is displacement time graph for a particle in transverse wave. If it's a displacement time graph, you can work out the peak-to-peak distance is the period, the amplitude is the height of the wave, and you can work out the frequency using f equals 1 over t. The question's asking which property of the wave cannot be determined from a displacement time graph, and that's the wavelength. You would need, for the wavelength, you would need the time axis to be distance. Okay? So the answer is D. That's the multiple choice done. Question 9 is a diffraction grating to determine the wavelength of light emitted by a laser. Light passes through the diffraction grating here, yeah, and the student observed a pattern on the wall 4 meters away, yeah. So you've got the central maximum, and then you've got the first order on each side, the second order on each side, and the student then measured this distance to be 1,350 millimeters. So let's draw that again. 1,350. So we know this side. We know this side of a right angle triangle, and we know this side of the right angle triangle. So we can work out theta, okay, using tan theta. So tan theta will be the opposite, 1.35 meters. That's the change in millimeters into meters divided by 4. Gives you the theta of 18.65 for 1 mark. So the student measured the distance that we talked about to the second order on one side between the central maximum and the second order. The diffraction grating is 300 slits per millimeter, so you can work that out by D equals 1 over 300. So you need that for the equation n lambda equals D sine theta. Okay, and so for D in meters will be 3.3 times 10 to the minus 6 meters. You get a mark for that. We want to use n equals 2 in this equation because we're looking at the second order position for this question, and then we've got to work out the wavelength, and from the table provided we're going to work out which color laser is being used. Okay, so the equation n lambda equals D sine theta is here. We know that n is 2, so we can divide both sides by 2 to work out lambda. That's D, we calculated already, 18.65, you put it into sine, and you get 532 nanometers, which is in the green range. Yes, the green range here is what we just calculated, so we know it's the green. The next question is talking about measuring the distance between the second order maxima and produce a smaller, if we measure the distance between the 2 second order maxima on each side, we produce a smaller percentage uncertainty in the wavelength. In other words, you would use the same instrument to measure the distance, so you'd have the same resolution, therefore the same uncertainty, absolute uncertainty, but with a larger distance, it would create a smaller percentage uncertainty. Okay? So, because the percentage uncertainty is half the resolution of your instrument divided by the distance, and the distance would be double. So you'd have, for that measurement, the uncertainty would be halved, and that should lead to a more accurate value of the wavelength as well. Okay. Question 10, it says astronauts placed mirrors on the surface of the moon. Scientists then can use the mirrors to monitor the distance between the Earth and the moon. The light from the laser is used with a pulse echo technique, so it means the light goes there, hits the mirror, comes back, and you can detect it. Describe how the distance can be determined using a pulse echo technique. So pulses are sent from the Earth and echoes are received from the mirror on the moon, and you get 1 mark for knowing what the pulse echo technique is, because the mirror reflects the light, and laser lights are intense enough for us to be able to detect them when they bounce off it. And then you measure the time for the pulse to go and come back. You don't need to know how they do it, but you just need to know that they have to do it to be able to then work out the distance by using the distance's speed times time. But the time needs to be divided by 2, which is a separate marking point, because you need to divide the time by 2, because the measured time is for the pulse to go there and for it to return. Yeah. So we want to know the distance, not the distance there and back, but the distance one way. And of course we know the speed of light in space is 3 times 10 to the 8, 3.00 to 3 significant figures. And that's how you get 6 marks. I think it's quite an easy-ish 6-mark question compared to what they can be as you go through the physics course. Here's the mark scheme again. If you want to stop it, you can have a look sideways. Once again, apologies for that. I really just want to get it out in time for your exam tomorrow if you're taking this exam. 2 of my students are. They went through today, so this won't benefit them. This is really for anyone else on YouTube, and also to have it there for the future. So there's the indicative content that you need to get the 6 marks. I'll let you have a look at that. And question 11, a student used steel ball bearings through a viscous liquid to investigate the relationship between terminal velocity and the radius. Okay, so the student used different radii ball bearings, so that's the independent variable. Describe how the student could make measurements to determine the radius of the ball bearing. So you'd use a micrometer ideally. Yes, you could use digital calipers, but the micrometer is the correct tool for this job. Measure diameter in several different positions or different orientations for reliability, because it may not be a perfect sphere. Yes, you need to check it, and then use the calculated mean value and divide it by 2 to change the distance to the radius. Don't forget that level of detail will get you the 3rd mark. If you miss that, you probably get 2 marks. They've then drawn a free body force diagram here, yeah, and they're ignoring the upthrust. Okay, the radius is 5 millimeters, so that 5 millimeters is 5 times 10 to the minus 3 meters. They want you to show that the weight of the ball bearing of that size would be roughly 4 times 10 to the minus 2 newtons. So we know the volume can be calculated using this equation. When you put the numbers in, to get the mass, you've got to multiply the volume by the density, which is provided here, to 2 significant figures. To get the weight, you then need to multiply by gravity. So in short, it will be density times volume times gravity, and that gives you, according to the examiners, 4.11 to 3 significant figures times 10 to the minus 2, and you've got to round it up to 1 significant figure to show that you have done your job, and that will get you the 3 marks. Okay? All right, so there, once again, there's their calculation. And there's the bullet points for what they give the marks for. Part 2, calculate the terminal velocity. Yeah, remember we're ignoring the upthrust. Yeah, they're giving you the viscosity. We know the weight is going to be equal to the drag. The drag is this, the weight is this. So the only unknown is V. So you put the numbers in, you get the answer, 0.24 meters per second, 2 significant figures, job done. Explain how the student can ensure Stokes' law will apply to the ball bearings falling through the viscous liquid. So basically, falling through the viscous liquid, we want to ensure we don't have turbulence. And to do that, we want to ensure the velocity is low. So you want to use smallish ball bearings. A small sphere ensures that we have laminar flow rather than turbulent flow. You can also use a wider tube or cylinder, because that would reduce the chance of turbulence, because turbulence is caused by friction between the solid objects and the liquid. And of course the tube itself is a solid object, so if you've got motion, the bits next to the side will be more create more of a friction between the liquid and the material that the tube is made from. Okay, so a wider tube will reduce it, and it seems like this is a common question for the linear. It's less common in the modular. Okay, question 12. The power of a lens in the human eye changes as the lens changes shape, and this enables a person to see objects at different distances. So a normal eye would be able to accommodate different distances, I think that's the right word. To change the shape, muscles in the eye put the lens under stress, change the shape of the lens, and here you've got a stress-strain graph for the eye for people of different ages. So a 30-year-old versus 23-year-old, and you can see the stress-strain ratio is higher for a 30-year-old. So stiffer, they have a stiffer eyeball. Okay, so the older person, the eye is stiffer, and we know that means the Young's modulus is greater, because the Young's modulus is the gradient of the stress-strain line. So give a reason for your answer. Why did you say it was stiffer? Because the gradient is steeper for the 30-year-old. There's the mark scheme for the first part, 12A, and then 12A2. Yeah, we've done. 12B we haven't done, and it looks like you have to calculate the power of lenses. So you can come back to look at the mark scheme after we have a look at the question. So this is the part B. The teacher was modelling the human eye. He placed an object 60 centimetres, 0.60 metres, from a converging lens system. A real image was observed, and the magnification was 0.5. So once we know the 0.5 magnification and we know U, we can work out V. And if you work out V properly, you'll see it's 0.3 metres. Keep both distances in SI units. And the teacher had converging lenses available to him of 2D, 3D, and 4D powers. So I'll call them power 1, power 2, and power 3. So once we know U and V, we can then use this lens equation to work out the power, which is 1 over F, which you don't need to then work out 1 over F, because 1 over F is the power. So we know the lens system has a power of 5 diopters. Get a mark for calculating that. That means he's used the 2 diopter and the 3 diopter in his lens system. So 2 lenses were used, because if you add the powers of those 2, you get 5 diopters, and lenses, the powers, you just add them. Okay, so 2 lenses, you add the powers. Hope that makes sense. That's 6 marks. Here we got a manufacturer gives information, the following information for a spring, follows Hooke's law up to 5 newtons, maximum extension without permanent deformation is 0.4 meters, which we don't do in this experiment, doesn't get that far. Stiffness constants are given with an uncertainty of 5%, that's K, and it can store up to 1.6 joules if you stretch it as far as possible, which means up to 0.4 meters. Yeah, a student carried out an investigation to test this information, so that's kind of like a mathematical hypothesis that it could be tested. Yeah. So she applied a range of forces from 0 to 5 newtons, and then measured the length and calculated the extension for each force, plotted the force against extension, and I've drawn the line of best fit because we're going to use it to work out the gradient and the stiffness. Delta Y would give me, on my graph, all the way to beyond the measuring points, because the gradient is the same. I'm then using a large triangle. Yeah, so the large triangle along the x-axis is using 300 millimeters, and downwards the distance is the whole full width and height of the graph paper. And a large triangle is one of the things that they look for on the mark scheme. Okay, so here is the mark scheme. Yeah, drawing a line of best fit, which we've done, calculate the gradient, which we can do, getting the answer in that range, which we can do. And then part B goes into more detail, which you can look at. Here's what they're looking for in grading it. And I think that's 6 marks. Yes. So you can stop the video whenever you want, have a look at your own answers and see how well you did. So determine the stiffness, so that's the gradient of the graph. I've drawn the line of best fit, I get a mark for that. 1 mark for showing my working clearly using a large triangle, and I got 20.0 newtons per meter with the line of best fit that I chose to draw. Then says discuss the extent to which students' results are consistent with the information given by the manufacturer. Up to 5 newtons, the line of best fit shows direct proportionality, therefore, because it's a straight line through the origin. So this is consistent with statement 1, yes, which follows Hooke's law. So I get 1 mark for that. Statement 2 is the extension of 400 millimeters is not reached in this investigation, so we can't really fully test it, yes, whether it will be deformed or not. So that's my conclusion for statement 2. Statement 3, K would be 21 plus or minus 5 newtons per meter. I got 20, so 21 plus or minus 5% would be 1.1, because 5% of 21 is 1.1 newton per meter. So just converting the 5% into the uncertainty in newtons per meter will get you another tick, yes. And then you calculate the gradient. You'll calculate the gradient if it lies within this range, which would be 19.9 to 22.1. That's the range. If you're within the range, you get another mark, and you comment on it. Then the energy stored at 5 newtons, which was the maximum that they went to, only got 0.625, and the statement 4 says that it can store 1.6 joules. For that, we would have to stretch it to 400 millimeters using the K value that I calculated, and you put the 400 millimeters in as 0.4, you square it, you would get 1.6 joules. So statement 4 holds in either case. At 400 millimeters, it would store the up to 1.6 joules. Okay, pretty good. So I think that would get the 6 marks according to where I have placed the ticks. All right, so I think I did this video before, and from 14 onwards, it's on YouTube already. But I'm not going to do it now because it's 10:30, and I might come back and do part 2 again. So I've done part 1 up to question 13. Hopefully it will record properly this time. The first time it was lost, so I'm having to record it again. So I hope you found it useful, even though I did whiz through it quite quickly. So do like it, share it, and let people who use linear, let them know that I'm starting to upload linear as well as modular papers, and that will help to get more people the videos that I'm making. And don't forget to like each video you watch and share it and subscribe. Thanks for watching. Bye for now.